All right, we now have another 4 spotlights in a row. The first one is policy conditioned uncertainty sets for robust MDPs, presented by Andrea Tiranzoni.
Hi everyone, I'm Andrea, and I'll be talking about policy conditioned uncertainty sets for robust MDPs. This is a joint work with Shangli Chen, Marek Petrick, and Brian Ziebert. So first of all, why do we care about robustness in Markov decision processes? Well, we know that MDPs have been successfully adopted for both modeling and solving complex sequential decision-making problems. One of the main practical complications is that the transition probabilities of these MDPs are often unknown. When these probabilities have to be estimated from limited amounts of data, the resulting estimation errors can have very bad consequences on the optimal policies that we compute. Unfortunately, this is a risk that is not acceptable in critical applications such as robotics or healthcare or finance. In all these cases, we need solutions that are robust in the sense that they provide guarantees on the optimal policies they compute, even in the presence of this uncertainty. In particular, in this work, we consider robust MDPs when we are given a finite amount and a limited amount of sample trajectories from some arbitrary reference policy. Here, the typical approach is to first build an uncertainty set, which is the set of all plausible transition probabilities according to the given data. And then we compute the robust solution as the optimal policy against the worst-case dynamics in these uncertainty sets. There's a problem. It is well known that when no restrictions are posed on the constraints that are used to form these uncertainty sets, the problem easily becomes intractable. Now, there's a form of constraints that allow tractability, and these are the so-called rectangular constraints. The idea is quite simple. We constrain the transition probabilities at each state or each state action pair independently of all the others. Unfortunately, these solutions, the price we have to pay for this tractability is that the resulting solutions are often too conservative to be useful in practice. And the reason why is that, very simply, we are assuming the worst case at each state action pair, which is an event that hardly ever happens in practical applications. Motivated by these limitations, in this work we propose non-rectangular uncertainty sets, which are defined using marginal features of entire state action sequences. So we suppose we're given a feature function that encodes the relationships between states and actions in our decision processes. Then we use feature expectations, so the expected sum of features that some policy achieves while interacting with the decision process, to summarize this interaction. Given these feature expectations, we define 2 forms of uncertainty sets. The first one is the set of all transition probabilities whose feature expectations under the reference policy match those that are measured from the data. The second one is more practical, and it's the set of all transition probabilities whose feature expectations do not deviate too much from the measured ones. Now, it turns out that the resulting robust optimization problem, so once again computing the optimal policy against the worst-case transition probabilities, where now these transition probabilities are forced to match or approximately match the feature expectations, has many interesting properties. First of all, we are now able to constrain whole trajectories rather than focusing on single states or single state action pairs. Thanks to these feature functions, we can now generalize across the state action space, something that is not possible using standard rectangular constraints. Our uncertainty sets are policy conditioned in the sense that whatever suboptimal reference policy we use to collect the data is not just ignored, but its bias is specifically accounted for in the learning process. Most importantly, we show that although a pretty hard subproblem arises from our formulation, we can devise a tractable and convenient algorithm to approximate its solution. And finally, we verify empirically that we indeed get less conservative performance than standard rectangular solutions. And well, if you're interested in knowing the details on how we solve this objective, please meet us at our poster 168 upstairs. Thank you. I made a mess. How do you? Wait a minute.
That's all right. All right, the next spotlight is learning convex bounds for linear quadratic control policy synthesis, presented by Jack Umenberger.
Hi, I'm Jack, and I'll be presenting joint work with Thomas Schoen on learning to control unknown dynamical systems. So we're interested in the task of learning to control. That is, if you give us some data from an unknown dynamical system, for example, some pseudo-random excitations of this inverted pendulum, then our goal is to learn to control the system. In this case, the stabilized upright equilibrium position. So in particular, we're interested in controlling linear time-invariant dynamical systems with the goal of finding a static gain state feedback controller to minimize the infinite horizon quadratic cost given Q and R. So when the model parameters A, B, and pi are known, this would just be the standard linear quadratic regulator problem, the solution of which is well known, but we're interested in the case where the system parameters are unknown. So in place of the system parameters, we have access to observations of inputs and states from the unknown true dynamical system. And then given this data, we can form the posterior belief over the model parameters. Then instead of optimizing the cost for fixed parameters, like you might do in LQR, we can optimize over the expected or average cost with respect to this posterior distribution. So this average cost can be difficult to compute, much less optimize. So we employ this Monte Carlo approximation based on samples from the posterior. These samples can be generated using Markov chain Monte Carlo methods, such as Gibbs sampling. And then to optimize the cost function, we form these convex upper bounds on the Monte Carlo approximation, and we proceed with iterative convex optimization. So the main technical contribution of the work is the formation of these convex upper bounds, and the crux of the problem is that our cost function involves these matrix inequalities. So all the terms in red are known. They're either sampled or given in the problem description, and the terms in black, they're our decision variables. And it looks pretty nice. It looks close to being linear, but there's this pesky matrix inverse here in the middle. So we just replace that with a first-order linear approximation, and that obviously gives us a linear matrix inequality, which is convex. But more than that, because this linear approximation lower bounds the matrix inverse, it also leads to a smaller feasible set, and it's this smaller feasible set that gives us our convex upper bound. So here we demonstrate the performance of the method stabilizing that inverted pendulum that I showed earlier. So here you can see the proposed method in pink, and recall the proposed method optimizes for the expected cost with respect to the posterior. We compare against some other methods. In green, you have a worst case method. So that's a robust controller that optimizes for the worst model in your data set, from your set, as well as another robust method in orange, which optimizes for the nominal model that you get from least squares. And we can see that the proposed method offers good performance, especially when there's little data available for learning. So if you're interested or like to know more, just swing by poster 166, and I'd be very happy to talk with you. I believe it's also upstairs. Thanks.